Welcome everyone to your first AP Chemistry podcast. This is Mrs. Benson and I'm super excited to have you here in class. And I do want to say that once again, if I haven't mentioned it in class, that the first 3 chapters we are going to go through very quickly, especially for some of you that maybe haven't had this for over a year. It might be a little quick, but remember when we get to chapter 4, everyone will be on the same page again and things will slow down a lot. So just stay with me, stay with me. All right, so we're going to start here with chapter 1, the scientific method, and you guys have been doing this through elementary school, so I don't need to go through all of this. I do want to make one point here with observation, and that remember that we're making observations, that we are making qualitative measurements and we are making quantitative measurements. And remember, qualitative is limited based on our vision. So we are observing and noting color changes or bubbling or gases being given off. And quantitative, we are actually measuring something. And then keep in mind, remember that science is ever going. And so we have this section here that you might have to continue to walk through this. And once you have a theory that's modified, you need to experiment and you just keep right on going. And then often new questions are going to arise. The metric system. It's a pretty involved metric system. The things that you're going to really need to know are the parts here right in the middle. And I would make sure that you review a kilo is 1,000 of a meter, and then all the way down to milli. If they give you anything else, they will probably give you what the scientific notation is going to be. You really don't need to worry too much about hecta and deca. I would just make sure that you understand milli, centi, deci, and kilo. And you'll be just fine, remember, with the base unit starting right there at 1. Okay, then we're going to talk about uncertainty in measurement. And we are going to have a lot of this in class, depending upon the type of lab that we are doing. And if you recall, the words down here, that precise and accuracy. So precision is something that it's an agreement with a value. So we might be really precise with all the values that we take in lab, but we're far away in terms of the actual value that we are looking for. So in terms of these dartboards, just kind of keep these in your mind, is that the first one, hopefully you're saying to yourself that it's neither accurate or precise. And the second one, with all these bullets here in this one little section, not near the bullseye where we want, but this is going to be a precise measurement. And then here, we could say that this is going to be both precise and accurate because we hit the bullseye and all of our measurements are there. Okay, the next couple sections, I think that we will talk a lot about this with the Remember This in class, and the worksheet that I gave you. So we have section 1.5, which is on our favorite sig figs, and then we have section 1.6, which is on dimensional analysis. And I have given you a worksheet on that, and remember that those answers are all scanned in on Schoology, so you can take a look at that and see how you're doing there with conversions. Reminder here about our temperature scale. We are obviously very comfortable with the Fahrenheit scale. We have Celsius and we have Kelvin. And remember that the Kelvin temperature starts at absolute 0, where matter ceases to exist. And you can see the difference of a boiling point of water, 212 degrees Fahrenheit, 100 degrees Celsius, and 373, very precise there in sig figs, 0.15 Kelvin. For all practical purposes, we would say 373. Okay, moving right along. Next, we talked about density, and we did a demo on density, so we did a little bit of that in class. You just have to remember that density is equal to mass, the amount of matter that you have, over the space that it takes up, which would be volume. And remember that that is grams per milliliter for units, or grams per cubic centimeter is another way to measure it. We need to remember that the density of water is 1.0 grams per milliliter, which is equal to 1.0 grams per, cubic centimeter. Okay, The next part, classifications of matter. Oh, there's the bell. Classification of matter. Matter is anything that takes up space. And the three states of matter, you should recognize that. That's going to be solid, liquid, and gas. See, this stuff is simple. You guys got this. All right, mixtures. We can have variable compound. We have heterogeneous and homogeneous. Remember that heterogeneous is that the composition is very different, and homogeneous is that the composition remembers the same. And the big part that you need to remember with homogeneous is that these are where our true solutions are at, a true solution. So a true solution of pop or milk will be a homogeneous. And distillation, we talked about that today in class with our question of the day, and we talked about that mixtures can be separated by that, and I think a lot of you understood when we talked about Coke refinery that it was based on its boiling point. Filtration, our next two labs are going to be on filtration, and that's just using gravity to be able to separate substances. And then chromatography, we are also going to do another little activity on chromatography, which is we're going to separate things out of their phases, and they all have to do with the movement through a system, and you will see this in the activity that we'll do in class next week, so don't worry about this. I will be talking more about that at that time. So when we talk about chromatography, hopefully movement through a system will make more sense to you. All right, you guys, that's chapter 1. That take me just 6 minutes, it looks like, so I'm going to keep on going. So chapter 2, atoms, molecules, and ions. So hopefully those are running around in your head there, atoms, molecules, and ions, and you're thinking that an atom is neutral. We have molecules where our elements are covalently bonded together, and then we have ions that have charges. So 2.1 history of chemistry, make sure you just read that over. It's not going to be specific on philosophers. Chemical laws, law of conservation of mass, and law of definite proportions, and law of multiple proportions. So law of conservation of mass, we did this all last year, that when you have a balanced equation, you are exercising the law of conservation of mass, that the number of atoms are the same on both sides. Law of definite proportions. So law of definite proportions is saying that it doesn't matter where I have water. I can have water here in Hastings, Minnesota. I can be out in Florida. I can be across the ocean. It doesn't matter where. Law of definite proportions says that every time I have water, I have 2 hydrogen atoms reacting or combining with 1 oxygen atom, and that is always going to be true. Law of definite proportions. If I were to say H2O2 and I add a 2 there, then I would have hydrogen peroxide. So that's going to have a 2-to-2 ratio. Then law of multiple proportions, you probably do need to remember John Dalton. For whatever reason, they like to throw him in a lot. So John Dalton had the law of multiple proportions. And you guys can see here with the example that I have here, the law of multiple proportions is just being able to analyze elements that are the same. So keeping in mind carbon monoxide, I have carbon and I have oxygen. Carbon dioxide, I have carbon and I have oxygen again. The elements are the same. So in my carbon monoxide, my ratio of oxygen to carbon is 1-to-1. Carbon monoxide is CO. Then I have carbon dioxide is CO2. And if I look at that same ratio in the same order, oxygen to carbon, I have 2 oxygen to 1 carbon. And it looks like I made a little smiley face there. Okay, so this is 1-to-1 and this is 2-to-1. And so it's just showing you the ratio between all of these. Okay, sorry, I had a little bit of a pause there. A student came in, so we were just talking about John Dalton's law of multiple proportions. Now, if I wanted to go ahead and add that I want to analyze NO2, Well, hopefully you would take a look and say, well, Miss Benson, you can't do that because this is carbon and oxygen, and this is nitrogen and oxygen. So you cannot apply law of multiple proportions when there is not the same elements involved. So this would be like trying to compare apples and oranges, and that's just not possible. Okay, next we have section 2.3, Dalton's atomic theory. Just kind of look through that. Again, like I said, just familiarize on a broad scale with the information there and the early experiments. Now, atomic structure, hopefully you remember a little bit about this of how to find protons, neutrons, and electrons. So you need to remember that in the nucleus, we have protons and we have neutrons. Remember that protons are positive, neutrons have no charge, and electrons are negative. And then we have these two substances, or particles, sorry, protons and neutrons are going to be in the nucleus of the atom. And then you have the electrons in the cloud that's on the outside of our nucleus. So if I take a look at argon, this is argon on my periodic chart. I can see its mass number is rounded to 40. Its atomic number is 18. So if its atomic number is 18, it identifies the element. That means I have 18 protons. And in this case, since there's no charge over here, that it also has 18 electrons. Subtract 40, the atomic mass, from the atomic number, and that's going to give me the number of neutrons, which is 22. So if I try one down here, go ahead and try selenium on your own. You can check your answers with me if you like. If I take a look at chromium, I look on the periodic chart, has atomic number of 24, mass number that they gave us of 52, and it has lost 2 electrons with its positive 2 charge. So I have 24 protons, and because I have a charge, it means that in the plus 2, I have lost 2 electrons, so that gives me 22. And I'm still going to do 52 minus 24 to get the number of neutrons, which is 28. And my overall net charge is plus 2 because I have 2 more protons. Up here, I forgot to do the charge. I have 18 and 18. 18 positives, 18 negatives gives me a net charge of 0. Okay, this right here, this iodine, really I should have that this is a negative. A lot of times books will, now at AP level, they'll just put the negative. It does mean that this is -1. So go ahead and try that one on your own. Okay, now we are going to take a look at isotopes. Atoms with the same number of protons but different number of neutrons. And so you can see here that I have my atomic number 6 is the same, so they are both carbon, but they are isotopes of each other because if I take a look, this one has 6 protons, 6 electrons, 12 minus 6, I have 6 neutrons. Over here, I have the same 6 protons because of the atomic number 6. I have 6 electrons. They have not told us it's an ion. And 14 minus 6 is going to be 8 neutrons. So you can see that they are different. And so they have the different number of neutrons. That makes it an isotope. So it happens that carbon is, if you're writing with a pencil, that's the one you're writing with right now. Carbon 13, carbon 14 are radioactive elements. All right, last section, 2.6, molecules and ions. So in a chemical bond, we have covalent, which they are sharing their electrons. So if we take a look at hydrogen, we know that hydrogen has 1 lone electron, and the other hydrogen has its 1 lone electron. Well, when they take a look and they do that, they each have 2 electrons, which is what they want to have to look like helium. So in order to become stable, they are sharing their electrons. Now in order for an ionic substance to do this, actually for covalent, you might want to put that this is between 2 non-metals. And here I have it between a metal and a non-metal. And you have a transfer of electrons. So plain old table salt, I'm going to change color here so you can see this. So plain old table salt, NaCl, hopefully you're saying to yourself that that's sodium chloride. And sodium is in family 1, it has 1 valence electron. I have chlorine, has 1, 2, 3, 4, 5, 6, 7 valence electrons. And how this is going to get stability is the sodium is going to give up its 1 electron to the chlorine, and so this is going to become a charged anion of -1. This sodium became +1 because it gave up its 1 electron. The +1, -1 makes it neutral, so that's how it's satisfying it to be an ionic bond for all of them to reach the stability. Then we have a sea of electrons, and that is the metals, plain old metals, plain old aluminum foil, however you want to take a look at it. If plain old aluminum is losing 3 electrons, and then you have another aluminum that's losing its 3 electrons, and there's no pattern here, you just have these electrons all over the place, and you have the sea of electrons, and that's how the electric current can go through. Jot yourself a little note just so you remember this, that cations, it's been a while I'm sure, cations are positive ions. How do they become positive? Is they lost electrons. The other side of your gold sheet had anions, and those were negative ions, and they gained electrons. So a little bit of review there for you. And this last section, do you remember how to write these chemical formulas or names? I'll post these answers at some point in class so you can check them over and make sure you remember how to do this. That's the last part of this section. There's lots of questions on that in the book if you need to review also. All right, that's it, you guys. Chapter 1 and 2 done in about 16.5 minutes. So hopefully you remember most of that stuff. Any sections you need to review, make sure you do that in your book. Looking forward to seeing you in class soon. Have a wonderful day.